Everyone. In today's lecture, we are just going to learn about the Poisson distribution, which is a discrete theoretical distribution. So, Poisson distribution is applied in many areas where, for example, to calculate the number of misprints on a page of a book, and also like a number of deaths due to the accidents in a month on National Highway 47 specifically here, not only for 47 in a national highway, and also like the number of breakdowns of a printing machine in a day, and also the number of vacancy occurring during a year in every departments. So these are just few application where we can apply the partial Poisson distribution. Okay, so let me define the Poisson distribution. So the probability distribution of the Poisson random variable representing the number of outcomes occurring in a given time interval or a specified region represented as T is P of x is equal to e power minus lambda power x upon x factorial, where lambda here is the average number of customers per unit time. Okay, so this is your probability distribution function of your Poisson. That is e power minus lambda power x upon x factorial, and x varies from 0, 1 to etc. infinity. And lambda is the average number of outcomes per unit time. And there is this Poisson distribution is a limiting case of a binomial distribution, which is like when at the end the number of trials are indefinitely large. Okay, so the Poisson distribution is a limited case of a binomial distribution under the following conditions. Like first one, in the number of trial is indefinitely large, and P, the constant probability of a success is in each trial is very small. That is P tending to 0. And the mean lambda is equal to NP is finite. So your P is lambda by N and Q is 1 minus lambda N, where lambda is a positive real number. So these points can be noted down for your MCQ purpose. Poisson distribution is a limited case of binomial distribution, and which scenario? Like they may give us this choice or like this choice. So coming to the next derivation of your MGF of a Poisson distribution. So as we know, the definition for Poisson distribution is like a definition of an MGF, that is finding an expectation of e power tx in the concerned distribution, right? So it is nothing but, as it's a discrete case, we'll go for summation x is equal to 0 to infinity e power tx p of x. And we know my p of x according to their Poisson distribution is e power minus lambda power x upon x factorial. So this range is for your x, which is varying from 0 to infinity. So just make your x together and leave it rest as a constant. So e power minus lambda is a constant which doesn't depend upon x. So put it out outside your summation. So left out group it as here lambda power. It is x lambda e power t power x by x factorial. Now make use of x is equal to 0 to infinity. So it's lambda e power t 0, 0 factorial, lambda e power t 1, 1 factorial, plus lambda e power t by 2 factorial, and it goes on. Now we can pull out the terms like e power minus lambda simplified, not pulling out, simplified. So anything for 0 is 1, so it's 1 lambda e power t 1 factorial plus lambda e power t the whole square by 2 factorial. It goes on, and this is like nothing but it's an expansion of e power t. So e power t is 1 plus t by 1 factorial plus t square by 2 factorial, and all goes on. Instead of t, I have here it is lambda e power t. So it is e power lambda t. So just as e is common, make it as a grouping. So it is pull your lambda out. So it will become e power t minus 1. So your MGF of your Poisson distribution is e power lambda e power t minus 1. So again, I have, as I said in the binomial distribution, you have to remember this one to derive the mean and variance based on MGF. Okay, and also for your MCQ purpose. So let me derive using your MGF, right? So mean is nothing but first derivative of your moment density function at t equal to 0. So here mx of t is e power lambda e power t minus 1. So this has to be differentiated with respect to t. So if I'm just differentiating, it is e power lambda e power minus t, and differentiation of this term is lambda e power t. Okay, so t equal to 0, substitute t equal to 0. So that it will become lambda e power 0 minus 1 lambda e power 0. So Here it will be 1 minus 1, it becomes entirely 0. So e power 0 is 1 and e power 0 is 1. So finally, lambda is the mean of the Poisson distribution. So I have to find the variance. To find the variance, I have to find expectation of x squared. So that I have to go for the second derivative of here MGF. That is mx of t, and at t equal to 0, we have to find it. So already we did with the first derivative here, just make use of that. So I have to differentiate that first derivative again. So lambda is constant, as this is uv, I'll keep it, use the formula of differentiation of uv. So it is e power t, differentiation of this one is e power lambda e power t minus 1, and again differentiation of this one will become lambda e power t, plus retaining your v power t, e power lambda e power minus t as minus e power t minus 1 as it is, and e power differentiation is again e power e power t. So make use of t equal to 0. I'm just making t equal to 0, this will become e power 0, and this will become e power 0, that will become 1 minus 1, it is again 0. So anything upon 0, and here it is lambda, and it is e power 0, and this is e power 0, and it is e power 0 is 1 minus 1. So what happens is this becomes 1, this becomes 1, and this is lambda, and this becomes 1, and here it is, you have the factor like, yes, it will become 1, and this become 1 again. Okay, so I got it like this is lambda plus 1. So already I have lambda, so lambda plus 1. So expectation of x square in Poisson distribution is lambda into lambda plus 1. Now I have to go for the variance. So you know the formula, expectation of x square minus expectation of x the whole square. So it is expectation of x square is just simplified. It is lambda square plus lambda minus expectation of x the whole square. So finally we'll get it as lambda. So the mean and variance of your Poisson distribution is nothing different. It is same as lambda. So next we'll go with the problem in Poisson distribution. So first one, on an average, a typist makes 2 mistakes per page. So what is the probability that she will make no error? That is probability of x is equal to 0. And if she makes 4 or more errors on a particular page, so it is probability of x greater than or equal to 4, because x we consider as number of errors on the page. So lambda, the average is, the lambda is a parameter in the Poisson distribution, average outcome. So average given here, it is 2 mistakes per page. So that is your lambda, and x represents the number of errors on the page. So you know the Poisson distribution is e power minus lambda, lambda power x upon x factorial, and x ranges from 0 to infinity. So now make use of your known term like lambda, e power minus 2, 2 factorial, sorry, 2 power 0, 0 factorial. So it is e power minus 2. So when I'm just making a p of x is equal to 0, I can find it. That is, no error on a page probability is 0.135. And coming to the second question, 4 or more errors. So 4 or more errors, probability of x greater than or equal to 4, as I discussed in the binomial distribution, you can write it as 1 minus p of x less than 4. So x less than 4 starts with 0, 1, 2, 3. Make use of it and add it and subtract it. So finally, you'll get the probability of 4 or more errors in a particular page. Okay, so coming to the next problem, the number of monthly breakdown of a computer in a random variable having a Poisson distribution with the mean equal to 1.8. So I have given with the mean lambda as 1.8. Find the probability that this computer will function for a month without a breakdown. Without a breakdown is nothing but number of breakdown is my x. So without a breakdown is x is equal to 0. With the only one breakdown, so it is p of x is equal to 1, I have to find. And with at least one breakdown, so it can be more than one, right? So it is x greater than or equal to 1. Okay, so p of x is equal to 0. So I know the Poisson distribution probability is e power minus lambda, lambda power x upon x factorial, where x varies from 0 to infinity. So this is here p of x, right? So make use of x is equal to 0. So substitute all lambda values and 0. You will find here probability where without a breakdown. And with exactly one breakdown, make use of x is equal to 1 and substitute in this formula, and you'll get the answer. And finally, last with at least one breakdown, so it is x greater than or equal to 1. I can write this as 1 minus P of x is equal to 0 because less than 0. We'll write this as 1 minus P of x less than 1. X less than 1 choice is only 1, right? Because it starts from 0. The range starts from 0. Only one choice. So that's directly written as P of x is equal to 0. Where we already computed this P of x is equal to 0. Substituted and subtracted. So you'll get the answer with at least one breakdown. Okay. So coming to the next one, it is known that the probability of an item produced by a certain machine will be defective is 5%. If the produced item are sent to the market in a packet of 20, yeah, this is the question which we already did in a binomial distribution. So the same problem can be done in a Poisson also. Let me explain how it is, right? Okay. So with a packet of 20, find the number of packets containing at least 2 defective, at most 2 defective in the consignment of 1000 packets using Poisson distribution. This question specifically given with Poisson distribution. If it is not specified, we can directly go with the binomial distribution itself. Okay. So the machine will be with a defective. Yeah, they produced a certain machine with a defective of 5%. So 5% in a 20 packet, right? So your lambda is the mean here. So your mean is NP. So N is this and P here. Your N is 20 and your P is 5%. So 5% is 0.05. So based on this, we can find my mean of the Poisson distribution. Because this is your binomial distribution, based on that, I can find the mean of a Poisson distribution, which is 1. So first one, at least 2 defective. At least 2 defective in the sense that P of x greater than or equal to 2. So I can write it as 1 minus P of x less than 0. So less than 0 will be the choice of x is equal to 0, x is equal to 1. So substitute x value as 1 in the general formula of P of x. What is your P of x? Here it is e power minus lambda, lambda power x upon x factorial. Similarly, this part. Finding at most 2 defective. So less than or equal to 2. So it is P0, P1, P2. Substitute in the formula and finally we will compute the answer. So coming to the next one, a manufacturer of a quarter pin knows that 5% of his product is defective. If he sells a quarter pin in a box of 100 and guarantees that not more than 10 pins will be defective. He guarantees, okay. So what is the approximate probability that a box will fail to meet the guaranteed quality? So the guaranteed quality is not more than 10 pins are defective. So what's the probability that will not fail? Okay. So they have given you that 5% of product is defective. So its P is 5, so 0.05 and Q is 0.95. So that using this I can make use of lambda. So lambda is equal to NP, which is 100 into 5 by 100, which is 5 again. So Poisson distribution, it is e power minus lambda, lambda power x by x factorial, and x varies from 0, 1 to infinity. So the question is, what is the approximate probability that the box fails to meet the guaranteed quality? What is the guaranteed quality? It is not more than 10 pills will be defective. So that fails in the sense that more than 10 pins will be defective. So it is probability of x greater than 10. So it is 1 minus P of x less than or equal to 10. Greater than 10, I don't want to go more because you have 100 pins, right? So make it refined. So I can make it like less than. It's 1 minus P of x less than or equal to 10. So it includes from 0, 1, 2, 0 here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have to find, we substitute it and make a simplification. It is 1 minus e power minus lambda. Here it is 5, right? So in substitute, finally you'll get the answer. Come to the next problem. So in a book of 520 pages, 390 typographic error occurs. Assume Poisson law for the number of errors page per page. Find the probability that the random sample of 5 pages will contain no error. So here average makers, we have to find lambda is not given. It is given that 390 typographic error occurs. So it is average is 390 upon 520 pages. So you got your lambda. And when the random sample of 5 pages will contain no errors. So 5 pages. So first I have to find no error. Then I have to make it for the 5 pages. So I'll find probability 1 paging containing no error. That is P of x is equal to 0. Substitute all the values of your Poisson distribution e power minus lambda lambda for x by x factorial. So here x is 0, right? So substitute accordingly so that you will find 1 per pages. If it is for 5 pages, just multiply it. So that is making the power of 5. That's it, right? So next, let me go for the next example, like similar to the binomial distribution, where the relation between the probabilities will be given, and we are supposed to find the mean standard deviation according to the requirement. Similarly, here it is given the relation is p of x is equal to 2 is 9 times of p of x is equal to 4 plus 90 times of p of x is equal to 6, right? So we know generally the formula for Poisson distribution and make use of x alone on each side. So e power minus lambda, lambda power 2 is to factor, which is equal to 9 times of x is equal to 4, right? E power minus lambda, lambda power 4 by 4 factorial, and plus 90 times of x is equal to 6. So it is e power minus 6 lambda power 6 upon 6 factorial. So in both sides you have e power minus lambda, lambda square common. So just cancel it. So it will become 1 by 2 factorial is equal to 9 lambda lambda square upon 4 factorial plus 90 lambda power 4 by 6 factorial. So on simplification, I can get an quadratic equation that is like lambda power 4 plus 3 lambda square minus 4 is equal to 0. I can make use of as a quadratic one and find the solution. So I got it as 1 and minus 4. Obviously, the variance, the mean and variance are cannot be negative. So your mean, your lambda is 1. So your mean and variance of this problem is equal to 1. And standard deviation is root of 1. It is again 1. Okay. So now let me go for next very important idea of fitting a Poisson distribution. Similarly, how we did in the binomial distribution, same thing we are just going to do. There we just made the same concept like fitting the given data into a binomial distribution. We did it like making in the sense that changing with the uh, fitting, yeah, changing in the distribution alone. So binomial distribution, you know, it is ncx p power x q power n minus x. Poisson is e power minus lambda, lambda power x upon x factorial. So we are going to use that one, and for to distribute frequency equally, we will make it n times of that. Okay. So first for that we have to go for finding a lambda. If a data is given, it is easy to find your mean. That is your lambda, right? Mean or variance according to Poisson distribution. So lambda is equal to summation fx upon f and 400 by this one. So it is lambda is equal to 1. So here n is 400. So you know the theoretical frequency is this thing. So this is your theoretical frequency. N p of x is equal to x. So n e power minus lambda, lambda for x by x factorial 400 e power minus 1. Because lambda we known, right? So this is again, this is also 1. No use of making lambda, right? Because lambda in anything power is going to be 1. So now I have to go for the all the variables of your x. So it is 0, 1, 2, 3, 4, 5. So starts from p of x is equal to 0 and into 400 we got it, and p of x is equal to 1. So apply it, we'll get it, and p of x is equal to 2, we'll get this, and p of x is equal to 3, we'll get this. And p of x is equal to 4, we will get 6.13, and p of x is equal to 5, we'll get 1.22. So to make a theoretical frequency, make a nearest round off, so it will become 147, and this will become again 147, this will become 24, this will become 24. And this will be equal to 6, and this will be equal to 1. So now add all the variables so that you will get it as, so add all the theoretical frequency, you will get the total frequency of 400. So this is what you have to fit the binomial distribution. Okay, hope I think you will be getting an idea about the Poisson distribution based on this video. Thank you for watching.